Yes. I will try to show from my computer. So please tell me if this works.
Hi everyone, I am Yichen Xu, and I'm currently pursuing my bachelor's degree at Beijing University of Post and Telecommunications. Today, it is my pleasure to present our latest work on implementing path-dependent JDT reasoning in the Scala 3 compiler. And this is a joint work with Alex and Lionel, and it is done during my internship at LAMP EPFL. Today, my presentation will consist of 4 parts. Firstly, I will introduce the backgrounds of JDT reasoning. Then I proceed to our work on JDT reasoning for path-dependent types. After that, I will discuss our work, and finally draw a conclusion of the presentation. First comes the preamble. The first question is, what are JDTs? JDTs extend the notion of ADTs users to encapsulate additional type information in data constructors. Furthermore, it enables extraction of such type information in pattern matching. Here gives an example.
Sorry, why is this so hard? There are echoes. All right, I'll try this.
Of a type-safe algebraic expression JDT. The expert class is parameterized with the value type. We define lit int for int literals, add for additions, and the tuple for pairs of values. The additional type information are carried in the JDT constructors. More specifically, the data constructors can specify the type parameters of the created data. For example, the lit int constructor asserts that the created data will be an expr of int, not expr of any a. This ensures better type safety. For instance, it prevents the user from adding a tuple to an integer. The evaluate function operates on the defined expr data type, evaluating the algebraic expressions to a Scala value. It illustrates another part of JDT, that is, extracting the additional type information carried by data constructors in pattern matching. For example, in the lit int case, JDT reasoning will find that since the expr of t is also a lit int, so the type parameter t must be an int. This allows the compilation of the case, since in the case body, we are giving an integer, but a return value of t is expected. And the example also illustrates existential qualification of types. For example, in the tuple case, when we know that the expr of t is also a tuple, we further know that there exist some types alpha and beta, such that x is an expr of alpha, y is an expr of beta, and t is equal to the tuple of alpha and beta. Implementing JDT in Scala is known to be difficult than vanilla functional languages such as Haskell and OCaml. This is because with powerful class and type system features, it will be possible to define open JDTs with complex inheritance hierarchy in Scala. The example illustrates a common pitfall of Scala JDT reasoning. Func is a trait representing functions and has a contravariant A and a covariant B type parameters. The class identity represents an identity function from X to X. Counterintuitively, if we know that a func of A and B is the identity, we cannot infer that A is subtype of B. This is because classes in Scala can be refined with variance. In the counterexample, we refine identity with a func of nothing and any, while a subtyping relation does not hold apparently. If we assume that A is a subtype of B in the match case, and it is any being the subtype of nothing in this case, we will have a soundless hole in the compiler, because we can cast anything to nothing. We can view JDT reasoning in Scala from the viewpoint of cohabitation. Cohabitation between some type S and T means that there exists some value of the intersection type S intersecting T. And this is exactly what we have in pattern matching cases. If we match a scrutiny of type S against a pattern of type T, then we will have X inhabiting both S and T, that is, a proof of the cohabitation between S and T. The task of GT reasoning is to extract necessary constraints from cohabitation. Here we use an example to better illustrate the point. Again, the evaluate function. In the lit int case, we will have an E with a type of expr of T intersecting lit int. By upcasting, this is expr of T intersecting expr of int. So expr of T and expr of int is cohabited. From this, since type parameters of classes have to be compatible, we can extract the JDD constraint T being equal to int. Although work has been done in Dotty to support JDT reasoning in Scala, the current implementation only supports type parameters and lacks support for path-dependent types. Path-dependent types is an essential type system feature in Scala. It can reference type members from runtime instances or singleton types of variables. We want to implement path-dependent JDT reasoning for two reasons. Firstly, the current understanding of JDT is based on the theory of path-dependent types, so implementing it can bring the compile closer to theory. Secondly, path-dependent types are a powerful type abstraction, so missing it will make the implementation incomplete and miss a lot of useful JDT use cases involving path-dependent types. Here we give an example that illustrates the usage of path-dependent JDT reasoning. The expert data type is parameterized with X, which is the value type, and has a type member size, which is the size of the abstract sentence tree of the expression. The size operator refines the size type member to a given type. We have two data constructors. The intlit constructs the integer literal. It has a value type of int and has a size of 1. The add constructor represents the addition. It accepts two expr of int and creates a new expr of int, with the size being the summation of the two sub-expressions plus 1. The swap function relies on both type parameter and type member JTD reasoning to compile. To see the path-dependent JDT reasoning beta, consider the add case. When tree is matched against add, we know that the value type of the tree is int, and we also know that the size of the tree is equal to n1 plus n2 plus 1. For some n1 and n2, they are the size of L and R respectively. Since swap preserves the tree size, we know that add swap R swap L is also of the size n1 plus n2 plus 1. Together with the knowledge that the value type is int, the code passes the type checker. Now we proceed to our work on path-dependent JDT reasoning. First of all, I would like to illustrate three main use cases of path-dependent JDT reasoning, and they are the use cases that our implementation aims at supporting. In the first use case, we would like to derive JDT constraints for the type members of the scrutiny and the pattern type when typing the pattern matching. In this code example, we would like to infer the JDT constraint that e.t is a subtype of int to allow the compilation of the code. Secondly, we would like to constrain path-dependent types just like what we do for type parameters. The p here can be viewed as a type tag. The path-dependent type p.t mimics a type parameter. We would like to derive the bound set int being a subtype of p.t, just like what we do if p.t is a real type parameter. Lastly, type members can be viewed as subtyping proofs. In the pattern matching case of the example, we have the variable e of the intersection type, as suggested by dot, which is a theory model of Dotty. Type members of habitated types are proof of the subtyping relation between the lower and the upper bounds. So we can get the subtyping relation, int expr being the subtype of expr of x, and we extract JDT constraint int being the subtype of x from this. For the implementation, we largely base our implementation upon the existing JDT reasoning framework. We'll explain our work from two aspects. Firstly, how we extend the data structures for managing JDT constraints, and then how we register path-dependent types. Firstly, the data structure. previous implementation used type parameter symbols to identify the constraint type parameters. However, unlike type parameters, which can be referred to use a single symbol, path-dependent types have a more complex structure. So we handle path-dependent types using path and type member symbols collectively. Secondly, type registration. Registering a type means to create an entry and associated internal representations in the constraint handler. Only after registering the type can we infer and store JDT constraint for it. For the type parameters, they are always defined in class and function definitions, so we can register them when typing these definitions. However, path-dependent types can be addressed from all valid paths. Paths can be parameters and locally defined values. So when and how can we register path-dependent types becomes a problem. We implement two type registration schemes to register path-dependent types properly. For details of our implementation, you may refer to sections 3 and 4 in our paper. We conduct experiments on our implementation. Firstly, to test the correctness of our implementation, we run the unit tests in the Dotty compiler on a branch. Our branch is able to pass all of the 8,345 unit tests. Secondly, we run the 10 test suites in Dotty benchmark to test the performance impact of our implementation. This figure illustrates the benchmarking performance of our branch. We report the relative running time before and after our work. We regard the previous running time as baseline and plot the ratio of the current running time by dividing it with the baseline. We observe that although the running time increases in a bunch of suits, the increasement is not big, considering that our implementation are adding additional logic and functionalities into the type checker. However, this suggests the room for the improvement of efficiency in the future. Finally, we discuss the relation between our work and the theory. We argue that our work will bring the compiler closer to the theory side. To see this, consider this concrete example. Our work enables the extraction of JDT constraint int being the subtype of A, which is not possible previously. Such reasoning already presents in Dotty's formal system, dot. Now we conclude today's presentation. Here we briefly list possible future work. You may refer to the paper for more details and explanations. First of all, we can unify the implementation of JDT reasoning for type parameters and type members. Currently, they have similar but separate handling logic. However, they have a shared foundation. JDT reasoning for type parameters can be modeled with type members, so it will be good to unify them. Secondly, when extracting JDT constraints, we will break down the types and try to find constraints for type members and type parameters, but sometimes it is impossible to break down the types. In such cases, we may still record JDT constraints for intermediate concrete types and utilize the constraints later. Finally, as stated before, the essence of JDT reasoning is extracting constraints from cohabitation. Pattern matching is only one source of cohabitation. By principle, it will be possible to extract JDT constraints for all habitated intersection types. Now let's conclude the presentation. In our work, we propose the implementation of path-dependent JDT reasoning, which is a missing piece of puzzle in the current implementation and can bring benefits both in practice and theoretically. What's more, we conduct empirical evaluation of correctness and the efficiency of our implementation. Thank you for listening. You can find the slides on this link, which is bit.ly pdjdt slides, or by scanning the QR code here. And see you in Q&A session.
Thank you for this talk. We are actually ahead of the schedule now. So the next talk is scheduled at 10. So that is in 4 minutes. So we'll wait for the 4 minutes just in case someone is coming from a different room and wants to attend. you can also use that time to ask your questions on the Discord channel of the Scala Symposium.
By the way, Seb, are you going to stream the next video as right?
Yes, since it worked
Yeah, it
on
worked
my
well.
computer, I use the same system. Yeah.
Yeah, great.
All right, it's time for next and last talk. So this here, share, play.
Hello, I'm Fengyu Liu. I'm going to present our paper on safe object initialization abstractly. This is a joint work with Andrew Notak, Enzo Shen, and Nguyen Gao Fan. The problem of initialization can be illustrated by the simple program. This program, when run, will print hello now instead of hello Scala. The cause of the problem is that the field name is used before it is initialized. Using a field before it's initialized is the cause of all initialization errors. When we care about self-initialization of objects, Joe Dufay, a former manager of the .NET Common Language Runtime at Microsoft, in one of his popular blog posts, mentioned that initialization errors is a source of consternation for programmers and a challenge for language designers in providing any guarantees for invariance, immutability, concurrency safety, and non-nullability. We can say that object-oriented programming is broken if objects cannot be safely initialized. For Scala, safe initialization has a particular importance because the safety of the dot calculus is undermined if there is no initialization safety. This example demonstrates the problem. We define a field B with a bad bound, which says that the type any is a subtype of the type nothing. Now, if we use the field B before it is initialized, then we can basically make any type A to be a subtype of any type B, but thus crashes the program at runtime. Using the field B after its initialization, however, is not a problem because in fact there is no way to inhabit the type except via infinite loop or throw an exception, which does not impact language safety. Let's examine the essence of the problem. In this example, initially this points to an object with no initialized fields. After the first line, the field self is initialized and it points to itself. Now, it is an error to select the field n on this dot self because the field n is not yet initialized, despite the fact that such field access is always permitted by the type of this dot self. So the lesson is that types are not enough. We need type state. Type states ensure that only a valid subset of the supported operations are performed for a specific state of a value. The problem of safe initialization is in essence a type state safety problem. To ensure type state safety, there are two choices. We can introduce type annotations, or we can perform type state inference. Type state annotations are verbose and incur burden on programmers, which make them less practical. For the adoption of safe initialization in daily programming, type state inference is the only valid option. So the real problem is how to develop a fast and sound analysis for type state inference. We take several recipes from past research. Here we introduce the two most important recipes. The first recipe is hypermonotonicity. Roughly speaking, hypermonotonicity is the idea that initialization state cannot go backwards. There are at least three different levels of monotonicity: weak, strong, and perfect. Weak monotonicity says that initialized fields remain initialized. Weak monotonicity does not enjoy transitivity. In contrast, strong monotonicity ensures that a transitively initialized object remains transitively initialized. Perfect monotonicity, in addition, ensures that the initialization states of fields are transitively monotone. We adopt perfect monotonicity in our analysis, as it gives programmers more freedom in using already initialized fields inside the constructor. The second recipe we take from past research. Local reasoning means that in the transitively initialized environment, the resulting value of an expression must be transitively initialized. Local reasoning is an important principle. It is very natural, close to how we reason about initialization in daily programming. Another reason is that it avoids whole program analysis. Thus, it gives rise to faster algorithms for type state inference. However, local reasoning is not free. Accepting local reasoning implies embracing three design principles, namely stackability, weak monotonicity, and scopability. Our analysis already adopts perfect monotonicity, which implies weak monotonicity. Stackability implies that all fields of a class should be initialized in its constructor. Scopability demands that there should be no set channels for accessing uninitialized objects. Control flow effects such as exceptions may break stackability and scopability. The analysis needs to ensure that only transitively initialized values can travel through set channels. With the recipes, now we can develop an efficient analysis for type-state inference. This is the abstract domain of the analysis for a simple language. The domain contains 4 kinds of abstract values: hot, cold, warm, and this. The abstract value hot denotes transitively initialized objects. It is the bottom of the lattice. The abstract value cold denotes objects of unknown initialization state, which is the top of the lattice. The abstract value warm denotes objects of class C with its own fields initialized, but not transitively initialized. The values V represent values of arguments to the constructor of the class C. The abstract value this denotes objects of class C currently under initialization. Omega here denotes the set of already initialized fields. Now, let's look at some rules of the analysis. As there are many rules, we only introduce the rules for method calls and mutation. In the rules, we use C to represent the class table and L to represent the value for this. This rule says that if the receiver of a method call is hot and the arguments are hot, then the result value must be hot. It takes advantage of local reasoning. The analysis does not care about what the method does exactly. This is one important reason why the analysis is fast. In the case where the receiver of the method call is not hot, but it is the abstract value this or warm, we need to apply this rule. This rule basically follows the method call and analyze the method body. This is possible because for the abstract value this and warm, we know the concrete classes of the underlying objects. So it is possible to resolve virtual method calls on them statically. Another thing to notice is that we currently always require method arguments to be hot, but the values for the receiver can be the abstract value warm or this. In another word, the analysis is parameter insensitive, but it is receiver sensitive. Here is the rule for mutation. In our simple language, we require that a mutation is always followed by an expression. Here you say that the mutation is followed by the expression E. We require that the value of E2 is hot. This is how we enforce perfect monotonicity in our analysis. Also notice that here, it does not matter whether the assignment is performed before or after the last expression E. In another word, our analysis is flow insensitive for expressions. At this point, you might think we have an analysis that works. Not quite. Some subtlety is hidden in the rules. Look at this program. To prove that it is safe using the rules, we would need an infinite proof which says that the result of the method call foo is some value v, while v is a fixed point for foo. In particular, v may take the value cold, which is the greatest fixed point for foo. It may also take the value hot, which is the least fixed point for foo. The safety of the analysis ensures that all fixed points are safe, but it does not specify how to compute them. We are only interested in least fixed points because they accept more valid programs. We use a well-known approach called co-inductive caching to compute least fixed points. The algorithm works by using both an input and output cache. When evaluating an expression, it first checks whether the value is already in the output cache. If it is, simply use that value. Otherwise, it first retrieves the value from the input cache and put it in the output cache. In case the value is missing from the input cache, the bottom value hot is used. Then it proceeds to evaluate the expression. If a recursive evaluation of the same expression with the same configuration is encountered, the value in the output cache will be used. Finally, we update the output cache with the actual value from the evaluation. This value will go up the lattice as the evaluation function is monotone. At the top level, the algorithm iterates until the input cache and output cache are equal, which means we have reached a fixed point. As a side note, fixed point computation for context-sensitive interprocedural analysis used to have a bad reputation for compiler writers because of poor performance. Our analysis is an exception because of local reasoning, hypermonotonicity, and selective sensitivity. In practice, we are unaware of a practical code that requires more than 2 iterations. Our initial experiment shows that for the DOTI project, the initialization check takes less than 5% of the total compilation time. One question that you might have in mind is, how does it improve the state of the art? Compared to the OOPSNA paper last year, a noticeable improvement is that the analysis removes the annotation requirement on class parameters. In fact, the annotation is never implemented. Thus, the initialization pattern of linking days to constructors is not supported. The new implementation supports this initialization pattern without the need for annotations. There are several other improvements which are less visible and difficult to quantify. For example, the abstract domain gets simplified. There are improvements in regularity and engineering simplicity, etc. Overall, we think it's a big step forward. With that, we reach the end of the talk. If you are interested in more details, please read our paper and feel free to reach out to us.
Thank you for our last talk of the day. So we'll now proceed with questions and answers to our various speakers. And as a reminder, for the you can ask your questions on Discord. So we have already 2 questions. Let me open the right thing here. All right, so the first question goes to Yichen. Scala 3 with explicit nulls also supports adding constraints to term members via flow typing. Do you think this could be unified with your mechanism, which adds constraints to type members?
Well, at the first glance, I think it cannot be directly unified because we generally consider type refs to represent path-dependent types. Which this means is that we currently add constraints for the type refs, but not term refs. But technically, I think if we are to unify the 2 things together, it is possible to use similar mapping techniques to record constraints for path-dependent terms. Yes, I think that's my answer.
Cool. Thank you.
Thank you.
Thank you. So our second question from Jacques Noyer to Alexander. I got a feel for how it would work for one kind of capability, and also that the same scheme could be used for introducing some other capabilities. But what happens when several capabilities are used together? For instance, are there several capture sets or different kinds of elements in the capture sets? What does introducing a new capability entail?
So as for the first part of the question, so when there are multiple different kinds of capabilities, they would all be members of the same set. So we don't really need to introduce any new kind of member for the set, right? In principle, any reference can be a member of the capture set, right? Like we have seen in the triple example. So it's not only direct capabilities, but it also things that could capture capabilities themselves that can be members of capture sets. Now for the second part of the question, which is what does introducing a new kind of capability entail? Well, that depends on the kind of capability. So if it was something like the I/O capability, then that would require significant changes to the standard library, right? We would need to change the language to support that. And also something like DB connection or file that would, well, we would need to structure a library around using something as a capability in order to provide reasonable safety guarantees, right? But other than that, we should be able to make anything a capability just by following appropriate or by using appropriate type signatures.
Okay, I see. Thank you.
Thank you. A question for Van Nguyen's talk. With the new implementation, is there still some escape hatch to disable the initialization checker if I need to for some reason? Not
Yes.
putting too much trust into the system.
Yeah, so there is. So if they don't want to use the system, they can, because it's opt-in, so they just don't use that -y safe init. And if they enable the system, if in somewhere they want to do crazy stuff, they can just use kernel unchecked. So that particular expression will not be checked. Yeah, so it's like in the tab system, sometimes people want to like remove all the constraints or remove the constraints of the system to do some more advanced stuff. So if they do that, yeah, they're on their own.
Thank you.
Thanks.
Thank you. We have one more question for Alexander. I'm wondering, how is the ergonomics of using the new capability-based system when you have to write wrappers for ill-behaved Java codes? Do you find it to be cleaner, or are there new hiccups?
So far, we have not actually considered. We don't have actually much experience with the capture tracking system, right? Which is why it is experimental, and well, not something that is part of the language proper. But in principle, I don't think that there should be any real problems associated with Java methods, because we should just be able to take rows annotations on them, and we should use them as indication of what exceptions should actually, or on what exceptions will actually be thrown by the definition, and then that will integrate just as well with the rest of the system as normal Scala definitions.
Thank you. I see that some people, so we were out of questions, but I don't know, I see people are writing more questions. So follow-up question, apparently. In the Java community, there's the opinion that checked exceptions are bad. How the new approach is going to improve the status quo?
Okay, just check whether the question is actually as to how. Well, we believe that the way this approach is going to improve the status quo is that if we add an easy way of expressing polymorphism, then that will mean that we can actually express accurate signatures for most definitions, and those signatures will actually also be easily understandable which is what we think was the biggest problem really with checked exceptions, because things like capture polymorphic map or like exception polymorphic map were just not expressible in Java, and that was by far the biggest problem. Now, of course, there are also other things to consider, such as expressivity, being able to express that, being able to abstract over what sort of exceptions some definitions throw. We have some plans for that that we haven't gotten started on yet, but we are thinking about these problems. And also, there are already things that are implemented in the language that should help with some of these problems. So, for instance, contextual function types should also be able to help us with some of the, should help us make the syntactic burden as small as possible.
Thanks.
Thank you. I see there's one more question, but I'll interject one for Guillaume in the spirit of fairness of, of questions. So as I usually ask when I see a paper that is very theoretical, but that touches on the practical system, has the theory behind this new paper already influenced or guided the practical implementation towards a better direction, or are they plans to?
Yeah, so I think I mentioned that the work on erasure is not something we can really change now that Scala 3 is out because of binary compatibility implications. So I studied like how we could improve intersection type erasure, and I could make a PR to change it, but then I will break everything. So I'm holding off on that until we decide to break the binary compatibility of Scala, which I will expect not to happen for a certain number of years. I guess right now is 5 years, but that might be optimistic. We'll see.
Thank you. So one more question for Pangwin then. Is there any work left to be done before we can enable the initialization checker by default in Scala?
Yeah, so yeah, I mean, we are about to next milestone is to bootstrap the Doti. I think it's coming soon. So we can enable that for Doti in the bootstrap combination. But there is still something left to be done, that is about the global objects. If we have global objects, they are like global variables. So initialization safety for those variables currently are not checked. So we're still working on that. So it's going to be a separate mechanism to check them.
Thank you. Looking forward to that.
Thanks.
All right. I think we are through with all the questions that have been asked on Discord. So unless something pops up, thank you very much, everyone, for giving the talk, submitting papers, attending the symposium. Also for bearing with me and the system, the technical difficulties we've been having. So enjoyed the rest of the conference. Feel free to keep asking questions or talk to the speakers in the Scala Discord. I'm sure they'll keep following it for a day or two. Yeah, that's it. Goodbye and until next year.
Thank you. Bye-bye.
Thank you.